All right, so the plan for today is to just keep working away on induction. And I moved your homework assignment back as of this morning. I don't know if you noticed, to Monday. So it was set on Wednesday. Since we're doing some more practice with induction today, the homework assignment is on induction. I'll give you guys some extra days to complete those. So some of the ones we do today should help with some of those homework problems, I hope. Yeah, so before we get started, any questions from anybody? Okay, so I want to just kind of first make sure the material from the reading quiz went okay. So you saw some examples where we may need to use more than one base case, for example, or we may need more than one domino to knock over the rest of them. So here's a similar example to one of the proofs that was on the video, talking about different ways that we can prove things. So if I want to prove, here's the sum of the first n cubed numbers, and I want to show that we can derive this formula for all values of n. So we go through and we have the base case and the induction step here. So this is not a correct proof over here. So I'm just kind of curious if you take a second to read the proof, base case, induction step, and let me know where you think there might be some errors in this proof. So let's start with the base case. I don't have a, let's see if I can open a quick poll here. Okay, I'm going to refurbish a poll from earlier. So here the question is, you can ignore the question about is this relation a function. Here what I'm asking is the base case correct? So it's a yes or a no, or I have no idea. So disregard this function thing. Do you guys think the base case looks good? Okay, I think just about everybody is in. So here were the results. So seemed pretty divided. Half the class said it's okay, half the class said no. And most people were not too certain about their response here. For somebody that said no, I guess I could probably take both of these answers here. It probably is okay, but it might not be explained in the best way, I would say, for the base case. For somebody that's said no or yes, yeah, so sorry, there was a question about the hypothesis. So this is just asking us to use induction to prove this. So basically it's saying if n is a natural number, then this is true, is another way that you could frame that. So does anyone kind of have a suggestion about what we could do to that base case to make it cleaner, more clear?
I said yes because the algebra made sense. I think the only thing I would add is that n is equal to 1, and I'd say 1 is equal to 1 when defining n, but I don't know if that's right.
Yeah, so we've got, let's let n equal 1. And then, so you were saying that you might want to substitute that in, if I'm understanding, you would want to substitute this in someplace where we didn't, or?
Yeah, on the at least in the last step, when it's the left side where it's n to the third is equal to the fraction, I would say 1 to the third is equal to 1.
Yes, I agree. So maybe this looks a little bit weird over here. We have like something general on the left side. So it's not actually true that this is equal to that, right? It's true when n is equal to 1. So kind of the right gist is here, but maybe the ideas are a little bit jumbled up. So one way that you might want to just clarify this is we have an equation, so we want to check that both sides are equal to each other when n is equal to 1. So you could just say something like on the left side, all right, on the left side, if n is 1, we just have 1 cubed, which is 1. On the right side, so you could kind of show this out if you wanted to. And then say, okay, since the left side and the right side both give me 1, base case holds. Maybe that's a little bit more clear. So I don't think that this is like, I would say this is nonsense. You don't know, this person doesn't know what they're doing. I think they actually do. It's more of a, I think this could be a little bit clearer type of thing. Okay, and any other thoughts about that? So then let's take a look at the induction step. So, right, this usually starts by let's state the induction hypothesis. Let's set it up. What is it that we want to show? And then let's see how this goes. So let me just ask the same question. Disregard the function part of this. The question here is, what about the induction step? Is the induction step correct? So again, give me a yes or a no, or I'm not sure. Okay, so here are the results here. So this one came in, this one came in with like half of the class, over half of the class saying it looks good. A couple people said no, someone wasn't sure. So sorry, I just saw a question come in about the base case. I would say, the base case is not solid just in terms of it wasn't explained clearly what is being checked here. I mean, they plugged n equals 1 into this side and got 1. What did you do with this side? Didn't really see that you did anything with this side. So really the goal here is to say, well, we need to plug n into both sides and make sure that we get the same thing. So with this one, the induction step here is without a doubt not correct. So there, okay, not to say like it is totally wrong, but there is something incorrect here. So we've got our induction hypothesis stated fine here. So that I'll just highlight in yellow. And then we kind of state what it is that we want to prove. We want to prove the same thing holds for larger values of n. So let's go ahead and set n equals k plus 1. Right, and that's the wrong step there. I don't know that this is true. If I did know that was true, then there would be nothing to prove here, right? So this is what we're hoping to prove. So just be sure that when you're working with this step, this formula that we're trying to prove doesn't go here. That's what we're trying to work to over here. And so if this person just X'd out that part of the proof, the rest of it would be okay. So there was just kind of this unnecessary thing that was added over here. This was a similar thing that came up on the reading quiz that you guys had as well. So just watch out for that. You should be starting with the induction hypothesis. That's all you're allowed to use. So I'm allowed to say that's true for values of k that are for values of k less than n. So I can say this by induction. And so using that induction hypothesis, we want to prove this. And if we start with that second line, then the rest of it would have been fine. So definitely resist that temptation to put on the right side the thing that you're trying to prove. It's good to keep that in mind, but that's what the goal is. We're trying to get to that point. And I would say that is probably the most common mistake with induction, is kind of using the thing that you're trying to prove and then just coming back into a circle with that. Any other questions about this example? Okay, so here is that same proof kind of cleaned up, but just presented in two different ways. And this is kind of what the video went into a little bit. So here is just kind of an explanation about saying, like, here's how we can check the left side and the right side, and the base case holds. So when you're reading things in the book, they might do things a little bit differently in some cases. So we've been doing this thing like, let's let n equal k plus 1, the very next integer. Sometimes people will use a different form of induction by just saying, like, n is anything bigger than k. And then saying, okay, n minus 1 is an integer which is less than n. So since we've assumed this is true for all integers less than n, and so here we're using induction for the case n equals 1, which is less than n. And it kind of goes through the same way. So the only difference here is they're using n plus 1 case to imply the nth case, where we have typically been using like the kth case to give me the k plus 1 case. But hopefully you see at the end of the day, right, it's just saying the integer, this integer knocks over the next one, whether I call it n minus 1 and the next one n, whether I call this k and the next one k plus 1, it's all the same thing. So that's kind of what it would look like with the k plus 1. And at the end of the day, it's whether you want to use n's or k's, and we've been using the k's. But you're welcome to use any method of induction that you like. Okay, so yeah, so this kind of summarizes various ways that you might state the induction hypothesis and state what it is that you're trying to prove. Were there any questions about that? Okay. Yeah.
Does all of this just come down to technique?
I mean, it comes down to notation really more than anything else. At the end of the day, it is the same technique that you're really doing in all of these cases. It's just, am I calling the integer, the next integer n and the previous one n minus 1, or am I using k and k plus 1, or am I using n and n plus 1? It's really just a notation issue, and the actual process would be the same in all of these. So it didn't affect the process here between these two. It was just one of them had n's and one of them had k's, really. All right. So then here was the next one that went through in the video. I tried to put a little bit more stuff in the video this time, just so we have a little bit more time in class to practice some new ones. But I do want to make sure that this one was clear. So the difference here, so this was this question where you want to make 8 cents out of 3 cent and 5 cent stamps. And the problem here is what we would like to use is the fact that if I know it works, for say like k minus 3 cents, it's not the domino right before the kth domino that's going to knock it over, but it's like 3 dominoes prior. So if I know that it works for k minus 3 cents, then the kth case would follow from that, because I could add a 3 cent stamp onto whatever worked for the k minus 3 case. So the issue here was we could prove the first case, n equals 8. We have a 5 cent stamp and a 3 cent stamp. Great. Case 9 doesn't follow from case 8 because I can't just add 1 cent onto that. So then we needed to say, okay, well, case 9 is a little bit different. We can use 3 cent stamps. And we still can't use induction yet. So for n equals 10, again, that is another special case. We could use 2 5 cent stamps. Once I've got 8, 9, and 10, then the idea is from 8, we can add a 3 cent stamp to get 11, and then 14, and then 17. And that handles all of those. And from the 9 cent stamp, we can get 12 and 13. That's not right. 12 and 15, excuse me, and 18. From the 10 cent stamp, we get 13, 16, 19. And between these 3 base cases, right, we can then add 3 cents and then get all of the cases out of that. So this works a little bit different than previous ones, but our method of induction will work the same here. The main difference was we just needed to prove each of these 3 so that then we can use them to knock down all of the other dominoes. And then once we get those 3 cases, then we can just say in the induction step, let's assume this works for all integers up to but not including n. And then if I want to prove it for the nth case, just take n minus 3 and add 3 cent stamp to it. So it's just kind of the structure of how induction is working here is a little bit different, but the concept is the same. Questions about that? Yeah, and yeah, so in this case, the reason why we needed to do 3 base cases is because we needed to go 3 steps backwards in order to prove the nth case. So that's how it worked there. Okay, and then here's where things were left with the last example. So here we have a recursively defined sequence, and the claim here is that this recursively defined sequence, we don't need to define it recursively. We actually could just write an explicit formula for the nth term. So we want to prove that this sequence, which we can define recursively, could also be defined more generally like this. So with recursive sequences like this, you typically need to prove as many base cases as special terms in the sequence. So A1 and A2 are special because they don't depend on previous ones, right? We just define them straight up as 1 and 3, and then all the rest of them are defined like this. So when we do the base case, we need to just verify that, okay, when I plug 1 into this formula, do I get 1 back? Yes. When I plug 2 into this formula, do I get 3 back? Yes, I do. So those cases hold. Okay, any questions? Okay, so then we come to the induction step. So now we're going to say, okay, let's assume now that this formula, this general formula works for all integers up to, but not including n. So we're going to assume now that this works for any value of k less than n. But again, what I can't do is assume that it works for n. We need to prove that. So that's what we're going to show. Okay, so we're going to show that this recursive formula is the same thing as this general formula. So I'm going to do it this way, where I'm going to just do it the same way I've been doing it, which is let's pick the next integer k plus 1. And again, you could kind of think about it using either one of these methods over here. So if I want to leave things with n, then what's important to note is we're going to need the 2 previous dominoes to get this one. So we would be able to use induction on the prior terms because we've assumed this holds for values of k less than n. Okay, or we could write it out in terms of the k notation. So these are, this is a choice that you're allowed to make. And let me just kind of show what those would kind of look like side by side. Sorry, maybe that's complicated. Let me just show kind of one of them at a time. So if we had this one using the k's, then what we want to show, right, is for k plus 1, it would be the same thing as saying 2 times n minus 1. Okay, where here our n is k plus 1. So we've used induction on this to say that ak could be written like this. We've used induction on k minus 1 since that is also less than n. So by induction, I know that that is equal to 2 times k minus 1 minus 1. And then it's just algebra, group things together. And that would be the same if we did with n. So some people like doing it like this, I'll just say, because this is the same formula that was stated in the theorem. So it's nice to have this proved in terms of n. That's how things are stated in the theorem. Some people prefer to do it this way. I don't care which way you do it. I've been doing it this way just because, from my experience, this tends to be what students like better. But again, you might feel differently. So feel free to do what you like. Questions? Okay, so then let's take a look at a couple of ones that I want to kind of walk through together and give you a chance to do a couple as well. So let's see. Yeah, so maybe one of these will help. So I'm going to take a look at question 8 on this. Might be a weird one to start with. So that's this one over here. Yeah, so we haven't done induction with an inequality yet. You have some on your homework assignment where you do need to do this. So let's practice one of these together, and then I'll give you guys a chance to practice in groups. So here we're looking at the product of a bunch of even factorials. So here we have 2 things. We have factorials and we have an inequality. So just keep in mind that when you see something like 4 factorial, this means 1 times 2 times 3 times 4. Okay, usually write it 4 times 3 times 2 times 1. I don't know why I did it that way. But the product of the first 4 integers. Okay, so let's go ahead and prove this. Okay, we're going to prove this using induction on n. Okay, usually, again, good place to start is let's explain the method that we're going to do, and then it makes sense why I'm looking at a base case. And so we want to do this for every positive integer, so we'll start with the first one, n equals 1. Then on the right side, we would have 2 factorial. We only have one term, which is equal to 2. And then on the right side, we have n plus 1 factorial raised to the nth power, which in this case would be 2 factorial raised to the first power, which is also 2. Okay, so in this case, for the base case, they actually equal each other, which is fine. Okay, any questions? Okay, then we come to the induction step. And so let's state the hypothesis. So let's assume that this formula works. So this would be k plus 1 factorial raised to the kth power. So we're going to assume that that formula holds. For all integers from 1 up to n. So I'm going to keep doing it our way with the case here. So I'm going to let n equal the next integer k plus 1. Okay, so then what we start with on the left side would be, well, let's plug k plus 1 into that formula. So we have 2 factorial times 4 factorial times dot, 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 2k factorial All right, so that's our left side. Any questions? Okay, so let's first, so the reason why I write things out typically like this is here we can see where the induction might come in. So I can see the first k terms in that product, and I know by induction, this is going to be less than or equal to k plus 1 factorial to the kth power. And then we've got this piece over here. This is actually not from induction. Okay, so the induction piece I put in red. So any questions so far? I think I flipped my inequality, right? Should be like that. Yeah, thank you. I think someone caught that. So on this part over here, I'm just trying to follow the comment. I can't use the induction hypothesis on that one yet, right? So I can use it on the first k terms. And now I've got this extra term that we just added because we just are now thinking about the next case. And so I don't need to show these two things are equal. In fact, they're not equal to each other. So what I want to do is if I can start to, and this is what happens when we're working with inequalities, if we can replace terms on this side with smaller values, then that's great, right? Then we'll get things that are going to get even smaller and even smaller and even smaller. And again, you know, what I'm hoping to show in the end, and let's not kind of lose sight of that, we want to show that this equality holds when n is equal to k plus 1. So that means we're hoping to show that this is like we're trying to get to that place over there, right? And let me kind of just write out what that would be. This means we're taking k plus 2 factorial right, k plus 1 times. That's what it means to raise it to the k plus 1 power. Okay, so we've got inequalities, we've got factorials, we've got exponents, we've got a lot of good math stuff going on here. Please let me know if something about this inequality is not clear so far. So if all else fails with these expressions, it might just be good to write out a bunch of these terms. So k plus 1 so I have k of those, right? K plus 1 factorials. And then 2 times k plus 1 factorial would then be, for example, 2k plus 2 factorial. Let me just slide this over a bit. So by definition, excuse me, all the rest of that stuff, right, would just be 2k plus 2 times 2k plus 1 times 2k, et cetera, et cetera, et cetera. Okay, any thoughts here about what we might be able to do? Like what do I need to do in order to make this stuff over here look like a bunch of k plus 2 factorials? So what would I need to multiply this by in order to get k plus 2 factorial? Right, so k plus 1 factorial would be product of the first k plus 1 integers. K plus 2 factorial is a product of the first k plus 2 integers. Right, and so just to kind of backtrack, right, I use my induction hypothesis just to get to this stage here. And all I've done at this point is just write out what that product looks like. I've written out what the product that I'm trying to prove looks like. And now I'm thinking about how can I take this product that I have from induction hypothesis and make it look like the thing I'm trying to prove. And my first thought is I've got all of these k plus 1 factorials at the moment. I need to get a bunch of k plus 2 factorials in the end. So what do I need to, what's the difference between these two factorials? So someone suggested to multiply this one by 2 in order to get this one. Don't think multiplying by 2 is going to work here. So here's k plus 1 factorial. Here's k plus 1 factorial. What's the only difference in those two terms? Yeah, so k plus 2 factorial has one more integer in its product, right? It's the next one. So if I can okay, so we're just using this idea over here that if I take k plus 1 factorial and multiply by k plus 2, it then becomes k plus 2 factorial. So let's keep that fact on ice over here. And let's next kind of think about this piece of it. So this would look like I had all these extra factorials here. Sorry. 2 to times k plus 1 factorial is just 2k plus 2 times 2k plus 1 times 2k and so on, right? That is I don't put the factorials in there again. Sorry. So I'm going to write it out like this. I'm going to just break this up into, okay, down here, I've got, there's one of my k plus 2 factorials, right? And now the part that I still need to work on here. So I'm just going to take the last k plus 2 terms and write that as k plus 2 factorial. And then I still have the 2 to the k plus 2, 2 to the k plus 1, so on. Okay, so any questions? You guys are kind of quiet. That's because you're all muted. So what's nice about inequalities is we have a whole lot of freedom that we didn't have before with equalities, right? With equalities, we really couldn't change the side. We couldn't do anything to one side that would change the value. Here, I can do whatever I want to the right side as long as I make it smaller, right? I don't want to make it bigger. So as long as I can think about how can I make this smaller and smaller and smaller, then we won't be violating anything. So as long as this line is bigger than the next line is bigger than the next line, we'll be okay. So over here, if we go from 2k plus 1 all the way down, excuse me, to k plus 3, we've got one term over here, two terms over here, all the way down to k plus 3. And the question is, how many of these terms would we have altogether? So if I start with k plus 2, I'm going to try and replace, these with something smaller. Where were we? Over here. So here's my first term, here's my second term. My question is, how many terms do I have between 2k plus 2 and k plus 3?
The only thing I'm thinking of is we have at least k plus 2.
Sorry, say that again, Mitchell?
I'm just trying to think of how are you able to specify something between a 2k term and a regular k term?
How am I able to express something? I think I missed the end of that with.
I guess I don't know how to know how many terms are in between there because I can't think of the 2k terms and the 1k terms being along the same line. I know that they are, I just don't know how that would work.
So, right, so we have k plus 3 times k plus 4 times k plus 5. We don't know what k is. Maybe here's another way that we can think about it. So here's my first term. Here's my second term. Here's my third term. Which term over here am I at? It's not going to be k terms. If I started with k and ended with 2k, right, that would be k terms. But I'm not starting at k. I'm starting at k plus 3. So we have a suggestion here for k minus 3. Close. So let me ask you this, right? I've got a 4 and I've got a 3 here. So why don't you tell me, like, what is the relationship between what I'm adding to k and which term it is? So like when I go from k plus 3 to k plus 4, that's 2 terms. I can take the 4 minus the 3 and add 1 to it. Right? When I'm at k plus 5, this is 3 terms. I can take the 5 minus the 3, which gives me 2, and then add 1 to it, right? Which is the same thing that I did here. If I had k plus 6, I would take that 6, subtract 3 from it, and then add 1, since I want to include the original term. So over here, I could take k, subtract 3 from it, and then just add 1 back to it. So we actually have 2 minus k, k minus 2 of these terms. So there's some arithmetic on that one. So you guys seem to be having some trouble with that arithmetic. Any questions? I don't think you're alone. Seems like that's universal. So that's nice to know sometimes. So you have homework. So that's the point of us being together right now, is this is the time that you guys can ask some questions so that you're able to be more efficient with your homework. Okay, well then I'll assume that that cleared it up. Good.
I was just going to say, honestly, I think this is one of those arithmetic situations that I'm going to have to sit down and play with to understand. I could sit here and watch you count that out all day, but until I sit down and do it, I'm not probably going to get that.
Yeah, so the question is, if we don't talk about it now, and you just went home and tried to do this on your own, would you be okay doing that on your own? Or there are some things that we should talk about now, because if it's not clear, then having 10 hours at home still might not clear it up. Maybe it does, sometimes it doesn't, right? And I guess we just never know. So the question that you should be asking yourself is, how could I calculate this? And then maybe do the counting later. But if it's not clear how to count these up, then you could have a whole bunch of time later on, but you'll probably still hit a roadblock. And sometimes that's part of the process, right? Is you just don't know until you hit it. But it's math. I mean, we've got k plus k plus k minus 1, k plus k minus 2, ... So there are different ways that you could try and count these, but you're just trying to count. So here's 1, here's 2, here's 3. How am I counting each of these? You could just kind of think about, I'm just taking this term over here and subtracting 2 from it, right? You're just trying to pick up on a pattern, really. That's what math is doing. So you can see here, the first term corresponded to a 3. The second term had a 4 over here. So really, it seems like all I'm doing is thinking about what am I adding to k, and let me just subtract 2 from it. So that's where over here, we can say here, since I'm adding k, this would actually be the k minus 2 or numbered thing in that list. Is another way to think about it.
So you're trying to pick up the pattern of the k minus 3 as to where it fits in the sequence.
Yeah, we're just trying to calculate how many terms are there between this one that we have over here and this last term that we had over here. So then when I actually do have this one, so this is like the k minus 2 term, that's another term, and this is another term over here. So altogether, between k plus 3 and 2k plus 1, this is a total of k terms in this product. Let me come back, place that over here. So we were starting with 2k plus 1 factorial, and now I broke that up into k plus 2 factorial because I know we're going to need to group a bunch of those terms. And then all of these terms, which are k of them. And notice that all k of these terms from k plus 3 if I replace each of these terms with k plus 2, it becomes smaller. Right? This line up here is bigger than the line below because every term in that product is bigger than k plus 2. So that's k plus 2 terms, right? That's why I needed to count up how many there were. I wanted to know how many k plus 2s can I now replace into this formula and make it smaller and not make it any bigger. So now we've taken this 2 to the k plus 2 factorial, and we've shown that we can at least say that it has to be bigger So we had a k plus 1 factorial raised to the kth power from the induction. And now we're going to replace all of that stuff with k plus 2. So that gives me k terms that have k plus 2. And now, great, you can see where we're going to get this k plus 2 factorial now. And then we still had this k plus 2 factorial. So there's kind of 3 components here, just to be sure. This red one came from the induction hypothesis. This one came from the fact that if I replace each of these terms with k plus 2, we get something smaller, which is 5. And then this just came from, we picked off the first k plus 2 terms over here. So really the thing that was critical here was taking each of these k terms, which are all bigger than k plus 2, and replacing them with the smaller value k plus 2. And now all of a sudden we've got our k plus 2 factorial. We have k of these. And then we have this additional k plus 2 factorial. So that gives us the k plus 2 factorial raised to the k plus 1 power. So I'm going to just place some of this scratch work that we did back at the end. And let me get it out of here. So this was the goal again. We wanted to show that this formula worked for k plus 1, and that's exactly what we just did. So again, the formula that we were trying to prove was this, and we did it now when n is equal to k plus 1. So we have a k plus 2 raised to the k plus 1. So once we've got the next domino knocked over by induction, we see this inequality holds for all n. So there was an induction step that hopefully seems a little bit familiar. The problem was it involves factorials, and that probably doesn't feel familiar. And it also involves an inequality. And so sometimes inequalities get scary. I like seeing them because it gives me more flexibility. I'm able to do more stuff on the right side. I don't need to keep them equal. I can make it smaller, and that was really key here. So that was, this green step was kind of the new part of this process here that might have been a little bit weird. Okay, so changed it up this time. Oftentimes we do an easier one, and then I send you guys off to do a harder one. I think this was harder one. It was 8. So let's see. I think that this one should be a little bit tamer over here. But let's see. So I'm going to break us up into groups, and I would like you guys to work on 4, which is again another inequality that has a factorial in it. And let me just say, just be careful about how we read this. This is 2 times n factorial. So it's not 2n factorial. So just be aware of that. So this is actually like 2 times n minus 1 times n minus 2, as opposed to 2n times 2n minus 1 times 2n minus 2. Okay, so here the idea is let's try and prove this for all natural numbers, for all positive integers n, using induction. I think it should be similar, but quite a bit easier, I hope, than the one that we did together, but we'll see. Let me open up some groups. Okay, so I'm just gonna have two rooms here. So I'm gonna have Lindsay will be in one room and I'll be in the other room. Both of those are open, so we'll see you in the breakout rooms. How did things go in the other room? Were you guys able to finish that one off, or?
We finished our base case and then we were talking about the induction step and exactly how we wanted to start. So we had like kind of like 3 different starts.
Got it. Okay, so I'll just say if you need to go, we are out of time. No, I guess I never know when people are coming or going anyway. You're welcome to go. If you've got a couple of extra minutes, then we can stick around and go through this together. We'll record it for those that need to go and put it up on YouTube. Okay, yeah, so let's see how this one went. I think we did make some nice progress with it. Oh, I didn't have it on this. Yeah, so let me just add a fresh page here. And so we were trying to prove 2n factorial is bigger than or equal to, help me out here, this was 2 to the n, was that the property? Yeah, for all natural numbers. Okay, so the base case went okay in the other room? Yeah, okay, so I'll skip that. So we get to the induction step. I'll put up the full proof on Canvas. But to focus on the induction step right here, we would assume that this inequality holds for all integers from 1 up to not including n. And then we want to show that this is therefore going to follow for integers bigger than k. And so I'll do it the way we did it in our group. They wanted to work with the next case, k plus 1, and use the kth case to prove the k plus 1 case. So for the k plus 1 case, we have 2 times k plus 1 factorial. And if you are kind of running into this issue of, you know, assuming the thing that you're trying to prove, it might be good to just write that at the end. And it's helpful to know what the goal is anyway. So that goes at the very end, not up here. And so sometimes, you know, you can play around with the ending and kind of see how induction might fall into that as well. But typically we start up here. And I think the first thing you might want to do is just write out what that equals, and maybe so that we can see where the induction hypothesis is going to come into play. So this, for example, would be 2 times k plus 1 times k all the way down to 1. So that is the same thing as 2 times k plus 1 times k factorial, which is the same thing as k plus 1 times 2k factorial. Any questions? So so far we've just kind of taken this thing on the left side. We want to show it equals this. So all I've done so far is just expanded that factorial and then regrouped terms so that now we can use that result. So I know that 2k factorial And then we kind of were looking at these two terms and we said, okay, I know that if I can slide a 2 in place of the k plus 1, that would get us to the finish line. And so why is it that we can do this? And since we know that k is bigger than or equal to 1, then k plus 1 is going to be bigger than or equal to 2. So here we have an inequality. So this number 2 is at worst going to be equal to k plus 1, but for larger values of k, we now just made this smaller, so it's okay. And now we've got the 2 times the 2 to the k, and that gives us the 2 to the k plus 1. And then there would be some explaining to do about, by induction, this completes it. But there were kind of two important parts here, and that was here we need to justify that we used induction, and here we need to justify why I'm able to replace the k plus 1 with a 2 over here. Okay, any questions about that? Okay, well, if you have any questions as you're working on your homework this week, just let Lindsay or myself know. Otherwise, good luck with your homeworks, and see you guys on Wednesday.